So we just took the test, and now that we're going out of the test, basically we're starting a new section. Technically, it's just the second half of chapter 2 that we're heading into here. But there is some variation, and so you'll notice some things are kind of coming back, but also some things are going to be totally new. And one of the big themes about the section that we're heading into is the idea that, we're going to have to be able to prove certain things along the way. Now, this does not mean formal geometric proofs or anything like that, but we still need to be able to provide certain specific evidences of how we can know something is true. And part of what we're going to be talking about today and going forward is going to be that kind of stuff. So today's big theme is the concept of continuity, continuous functions. So the function that you see up there right now, it's not a continuous function. We can say that the whole function, if we describe just the function as a whole, it's not continuous, but it is continuous for parts of it. There are specific places where it is not continuous. That is, there are specific locations where we have a discontinuity. Now, as you take a look up there, you'll notice in the bottom right-hand corner, this graph comes from page 119. It's figure 2, so you don't need to copy down the whole thing. You can just make a note of that, and then you can put it into your notes later if you wanted to. So we want to be able to describe what is happening at each of the values where we do have a discontinuity. So what is one value where you see a discontinuity here? 3? Yeah. There's a big one there.
And 5.
Now, 5, okay, I hear 5.
And -1 and 6.
No, it's just 1.
And I do see at 1, yes.
That's what I meant when I said -1.
But that's the only ones I see because we're really just given the x values here. Now, notice here though, we got to describe what is happening at each of those. So like, how would you describe what's happening at x equals 1? Yeah. At x equals 1, that is a hole in the graph. I'll give you some terminology for that later, but we'll also call that a removable discontinuity. It's called removable because the graph is the same graph as it always is. It doesn't affect the overall curve. It's just that that one point has been removed. All right. How would we describe what's happening at 3? Well, at 3, notice it's basically like we are at this point here, and then we jump up to that point. And so we actually call it, uncreatively enough, a jump discontinuity. All right, and then at 5, what would we call what's going on at 5?
Displacement.
Well, notice you got another hole there. And so, we'd still call that a hole. The fact that the point is up here doesn't end up changing that. All right, so we got to get a little formal definition in here then. And so a function is considered continuous at a point if the graph of the function is connected there. This is kind of an informal definition, but it's a very good one to put into your notes. A function is not continuous at a point if its graph has a hole or break at that point. And we'll see some examples of those here in a moment. All right, and so knowing that it's not continuous if there is a hole or a break in it, that means that there's actually 3 main types of discontinuities that we can run into. They are the jump, the asymptote, and the hole. Notice that the hole is also called a removable discontinuity. This can be worth adding to your notes as well. So the jump is a sort of situation where it's like a vertical break. So you notice there's a section of the graph there where there is no graph. The asymptote, at the asymptote there is no value, hence there's a break there. And then of course the removable, there's actually a hole there, and so we're skipping a point again. All right, and so if we have these 3 main types of discontinuities, I want to practice, make sure that we got the idea down and see some examples where we have these discontinuities showing up. And so here's another graph. You'll notice that this graph is from page 127, number 4. So if you want to be copying down the graph into your notes later, you can just go to that page in the book and do so. But for now, go ahead and take a look at it and write down for each point where are the discontinuities, and then what type of discontinuity is that at that point. All right, so as we take a look at this graph, the very first discontinuity that we're going to see is happening at -2. In that case, notice that we go from a value up here and then there's space between them. Since there's actually space between them, that is vertical space between them, then that means that we would call that a jump discontinuity. So that's a jump there. What about, let's see, the next one would then be at 2. What would we call 2?
Jump.
Yep, that is also a jump. Because again, we got that vertical space between them. Next discontinuity from there would be at 4. What type of discontinuity do we have at 4? Looks like asymptote. I mean, we don't have a way to prove that necessarily because we're going to assume that they both go up forever, up to infinity. And so then, yes, that would be asymptote. All right, and then finally, for 6, what type of discontinuity is that? It is jump, yeah, because again, we have that vertical space between our two endpoints. So that is also going to be a jump. Now, you notice that all of these were either jump or asymptote. None of them were just whole, because although these graphs have open dots in them, in order for it to be a whole, it would basically have to be the same on either side. You know, we're flowing in, flowing out the same. If you want to be technical, the limit from the left would be the same as the limit from the right in order for us to call it a whole. A jump is when the limit from the left is different from the limit from the right. Now, those limits, though, actually do enter into this concept of continuity, though. Because in order for something to be continuous, then we can think about the limit from the left heading into a point. Like I'll use 0 here as an example. The limit heading in there from the left, of course, has to equal the same thing as the limit heading from the right in order for it to actually be continuous. Otherwise, it's jumping someplace. But there also then needs to actually be a value at that point that they're both approaching. So in other words, there's not a hole that they're approaching in those limits. And so then that allows us to then come up with a formal, more mathematical definition of continuity. And that's what this is, and so that's why this now needs to go into your notes as well. This also shows that we can have continuity just from the right and just from the left as well. Just like we can have limits from the right and from the left. All right, so you've got these into your notes, and I do want to just make sure that you really thought about what you wrote down, though. Notice what these are saying. The limit as x approaches a. So in other words, as we approach it from the left and from the right, it equals the exact same thing as the actual value at that same a value. So in other words, like I drew on that previous picture, if I come at it from the left and come at it from the right, I'm approaching where the actual value is. And so we'll actually see some examples of this also going into action here. So let's actually take a look at one of those. We had some graphs earlier where we identified where the discontinuities were. We're going to go back to those. So this is that first graph that we saw earlier. Now we already know that it's not continuous at these 3. But it could be continuous just from the left or just from the right there. Or it could just be not continuous from either side. And so take a moment, look at 1, 3, and 5, and think about, is it continuous from the left, right, or neither there? All right, so let's take a look at each of these. For the first one, for x equals 1. All right, the limit from the left, does that equal the actual value at 1? No, because what is the value at 1? There isn't one, right? Because there's a hole there and nothing to replace it, there is no value there, and so, of course, it cannot equal the same thing. So, no, that one is not continuous from the left. Is it continuous from the right, though? No, for the same reason. So, this one is neither. At x equals 3 here. Okay, is this one continuous from the left? Yes. Well, as I'm following it down, I'm approaching wherever this point is, and notice we actually do have a value there. So yes, it is continuous from the left. Could it be continuous from the right as well? No. If it were, we'd have some issues there because it can't be continuous from both the left and the right, but not continuous. And we already know it's not continuous there. All right, and finally, at 5, Is it continuous from the left?
No.
Well, as I'm approaching from the left, I'm approaching this point here, but the actual point is up there. I'd have to be approaching that with my limit. And so that's why the answer there is no. It is not approaching from the left. Is it approaching from the right?
No.
No. And so that one is neither. Okay? Kind of got the feel there, I hope. And so let's apply that to the other graph that we looked at earlier, and it's for discontinuities. So again, for each, think about, is it continuous from the left, right, or neither? All right, so first up at -2. Is it continuous from the left? No, because as it's coming from the left, it's approaching this value, but there's a hole there, open hole there. Is it continuous from the right? Nope, because again, we got a hole there, so that one is neither. Okay, at x equals 2, is it continuous from the left?
No.
Nope, open circle there. Is it continuous from the right?
Yes.
Yes, because it's approaching a closed circle, so there's actually a value there, so that's approaching from the right. Okay, x equals 4. Is it continuous from the left?
Yes.
Well, this was where a few questions sometimes can come up. So the limit from the left is approaching infinity, right? Okay. What is the value at f of 4? In other words, if I go straight up on 4, what value do I actually hit?
Never.
Nothing. There is none, because there's an asymptote there. It approaches it, but it never actually crosses it. And so from the left, it approaches infinity. From the middle, it approaches nothing. There is no value there. And so that one is neither.
Oh,
right.
because it doesn't cross 4?
Yep, exactly, because it doesn't actually cross 4. And same thing happens on the right side, of course, there. And at x equals 6, is it continuous from the left? Nope. Is it continuous from the right?
I don't think so.
Nope. Because the point, the actual value, is right there, and our limits would have to be approaching that. And so this one is also neither. All right, one last thing coming out of all this information is that you notice that these discontinuities are tending to occur with piecewise functions. And that's how we tend to end up with all the jumps and things like that in there. And so there are certain function types where we can just look at them and know this one will not have a discontinuity. There's no jumps in a linear function, for instance. And so there's certain ones where we can know that we're going to be good. That's what this list is all about. This is a list of all the different types of functions that are continuous. But please notice the detail. They are continuous at every number in their domains. That's why rational makes the list. Because rational, of course, that's like 1 over x. It's not a continuous function. It has an asymptote in it. But the asymptote is not part of its domain.